like if we just
isn't it?
from 140 So where's the extra charges because
Oh wait, I just realized that's good. That's joules. So we're gonna have to convert this from joules to joules. We're gonna multiply this number by this is gonna be 142 joule over kilojoules per energy. Right? Makes sense. Did you make it bigger? You got why we multiply by 1,000. You see it? This one's in kilojoules,
right.
and this one's in joules, so I have to make it the same, so I multiply this one. So this is in kilojoules. So this is. This is what I got. This is what I got, but this one's in joules per mole. Let's just make sure. Oh, it's not the same as they got. 0.02. But that's still. They got. We got like. We convert this to 718. They got 163. What if we change this?
A couple of things here. The entropies that are given are the absolute entropies. So what is given in the table is not delta SF. What is given is the absolute entropy. So you have to first calculate delta SF. You're given delta HF. And then you do delta GF is equal to delta HF minus T delta SF. So what reaction should we look at for delta SF? We want to calculate the entropy of formation of ozone. So what reaction should we be looking at? Lauren, O2? I cannot hear you.
O2 to O3.
O2 to O3. We have a problem here. We have two oxygens on the left.
3 and 2.
I want one here, so I'm going to make this 3 halves. Okay? Now, you're given the absolute entropy of ozone. You're given the absolute entropy of oxygen. So you should be able to calculate the entropy of formation of ozone. Products minus reactants.
So that's how we're changing entropy. Oh, this is a how about minus 68?
you should get minus 69.8 joules per mole per degree. The entropy of formation of ozone is minus 69.8 joules per mole per Kelvin.
So what we did was like, what's in this topic here, you want to know so then when you put the thing here, you're going to have to keep a water. But then you're going to have to balance it between the sides. So to balance it, you're going to have to multiply by 2 so that the 2 is going to... Yeah, so then you take this number and you because you always multiply these numbers by
Questions?
so because above the each bar, they give it to us. Here, they give us the because the edge and the information. Yeah, you need to always give us the absolute entropy. So you have to change the absolute entropy of variation. Because to get the change of fields, variation, you have to have both.
Okay, so the Gibbs free energy of formation is 163 kilojoules per mole. Yes, Lauren.
So when you're doing the calculations, you keep it in Kelvin.
It doesn't matter, joule per Kelvin. Oh yeah, I mean, all the the delta G. This temperature here has to be in Kelvin always. Yeah. Questions? Which should correspond to the value in the first table, right? Questions?
1.68 times 10.
I may have made a mistake, or you may have, I'm not. Key point here is that you understand how to do the calculation. We'll worry about the details later. All right. So let's go back to our outline here. Remember, our ultimate goal is getting delta G reaction. We're going to get that from delta G naught reaction. And we're going to get to the delta G naught reaction from the Gibbs free energies of formation. And the Gibbs free energies of formations we're going to get from the enthalpy of formation and the entropy of formation. How do we go from here to here? The answer is this. You look at the Gibbs free energy of formation of the products minus the Gibbs free energy of formation of the reactants, and that gives you the standard Gibbs free energy of the reaction. So could you take a few minutes and do this problem here, please? Okay, so look at the first table. The first table has the Gibbs free energy of formation of all the substances in this reaction.
There's a table right here. And then you take it and just add this products and you subtract it from the formula.
It's not showing correctly.
For CO2, is that a negative sign?
For
The standard model gives energy?
yeah, minus 394.4.
And O2 is 0, right? O2 is going to be 0. It is. It's 0 because it's in.
Yes. The table does not have oxygen. It's 0. Yep. And the answer is minus 818 kilojoules. Okay, let's look at the answer here.
So, for the standard molar Gibbs energy formation and standard molar enthalpy of formation, anything in the stable state is 0.
Right.
It's not true for the entropy.
Right. Entropy, is not entropy of formation. It's absolute entropies. That's what's found in the table. Yes, Angela.
Just go to the chart, please. Didn't say it was a negative. It never
Oh.
looked like a negative.
Okay. Sorry.
What is the answer for that one?
The answer is negative 818 kilojoules. All right. Let's go to the outline again. Okay, so this is one way to calculate delta G naught reaction. Another way to calculate delta G naught reaction is to calculate delta H naught reaction and delta S naught reaction. Once you calculate that, you can use this relationship here. Where did this equation come from? Definition of Gibbs free energy, G is equal to H minus Ts. Okay, can you go ahead and calculate delta G naught reaction for this reaction? Same reaction, different method.
So you go to this is so even that sign that is major.
Is that a negative control one?
Yes.
If you scroll up to the tables in there,
Yes. That's the enthalpy of formation. And I'm going to scroll up to the entropy of formation. Sure.
Did you just find this for the reaction? I did find it for X minus reaction. So this is definitely the entropy integration or I'm not sure about changing.
So you should get the same answer that you got in the previous method. So here's my working of the problem. Delta H naught reaction is minus 890. Delta S naught reaction is minus 242. And delta G naught reaction is minus 818.
Is it?
Questions? Yes, Tiffany.
I was just a little confused, like, you know how in the last, the ozone problem, we had to convert the SF to delta SF? How come we didn't have to do that here?
You could if you wanted to, you would end up with the same answer. But in this case, very good question, okay? So supposing you have A plus B going to C plus D, my favorite chemical reaction. You can say delta S for this reaction is equal to S of C plus S of D minus S of A plus S of B. Okay, these are absolute entropies. These are given in a table. If you want, you can prove and it's just simple algebra. I have never proved it, but I know that this is going to be true, that delta S CF plus delta S DF minus delta S AF plus delta S BF. If you calculate the entropy of formation of the products and subtract the entropy of formation of the reactants, you'll get the same answer. But why do this when you can do this? These values are already given in the table. Very good question, Tiffany. Bless you. Yes, Lauren.
So if we've been given a table with entropy formation,
Very unlikely. I mean, I would have to spend a lot of time to create a table of entropies of formation.
but that would have given the same value.
Right. Okay, but it's better to have the absolute values. So you will always find absolute values for the entropies. All right, let's go back to our outline. Okay, so why are we interested in delta G naught reaction? What it tells you is if a reaction is conducted under standard state conditions, it tells you if the reaction is spontaneous or not. So the reactants must be in their standard states, the products must be in their standard states. But really what we are interested in is delta G reaction, because it is very, very unlikely that the reactants and products are going to be in their standard states. I know I'm skipping this information, we'll come back to that later. So the question is, how do we go from delta G naught reaction to delta G reaction? And the answer is that the Gibbs free energy of a pure substance depends on pressure via this equation here. Where did this equation come from? You will learn that in your first physical chemistry course. We spend about one lecture deriving this equation. We're not going to derive this equation. You're going to take it for granted that when you increase the pressure, the Gibbs free energy of that substance increases, and it's a logarithmic dependence, and the bar on top indicates that it's a molar quantity. So this is the Gibbs free energy of the substance under standard state conditions. That's at 1 bar. And at a pressure other than 1 bar, this equation gives you how the Gibbs free energy changes. This relationship is what is key to go from here to here. We're going to derive this equation here, delta G reaction is equal to delta G naught reaction plus RT natural log of Q. Very, very important equation. That's how you go from here to here. This tells you how to calculate the change in the Gibbs free energy at non-standard state conditions. To do this, to derive this equation, you need this equation here. Okay, so let's derive that. So A plus B going to C plus D. Delta G of the reaction is the Gibbs free energy of the products minus the Gibbs free energy of the reactants. So for each of these substances, we're going to use this equation here. For A, B, C, and D, we're going to each individually use this equation. So a delta G reaction is going to contain the molar Gibbs free energy at standard state conditions for each of the substances. Here are the products minus the reactants. This term here comes from this term here. This set of 4 terms come from this term here. Okay, we're doing simple algebra here. And then we're going to say that this whole term here can be written as delta G naught reaction. That's the Gibbs free energy change when reactants in their standard state go to products in their standard state. And now I can write the delta G reaction is equal to delta G naught reaction plus, I'm going to take the RT out. And now I have C log PC plus D log PD minus A log PA minus B log PB. How did I go from this equation to this equation here?
We put the A up, use the log rules.
I use the log rules, which say that if you have log of x to the power y, that's equal to y ln of x. Okay, I use that rule to go from here to here. And then how did I go from here to here? I used another log rule which says that log of xy is equal to ln of x plus ln of y. And I have the final equation that I want. This is the partial pressure of the products divided by the partial pressure of the reactants. And that quantity we define as the reaction quotient Q. So if we know the partial pressures of the reactants and products at a given time, so we know all of these quantities, and if we know what delta G naught reaction is, then we can calculate delta G reaction. That is our goal. That was our goal. We want to know what is delta G reaction is. How do we do that? We use this equation here, but we need to get delta G naught reaction. Delta G naught reaction we get from delta G naught formation, and the delta G naught formation we get from here. Can you please, yes, Lauren?
So you said Q is equal to the partial pressures of all of the products of the reactor.
Right, with the appropriate superscript. Can you take a couple of minutes and write out the equation here, but don't solve it? So don't solve the problem, just write out the equation. So what does it look like? What does the equation look like? What? Okay, here it is. Questions? Yes.
If, is this only in bars? You have to in bars.
You can work with atmospheres. Whatever you choose, be consistent, exactly. Lauren, question?
Why did you multiply 33 by 1,000?
Because that's in kilojoules. Everything, the R is in joules.
Okay.
So here is a visual diagram that summarizes everything that we've talked about. We want to get delta G reaction. That's our goal. Because why? It tells you if the process is spontaneous or not, if it's at constant T and constant P. How do we get delta G reaction? We get it from delta G naught reaction using this equation here. How do we get delta G naught reaction? There are 3 different ways of going about it. We'll talk about this on Wednesday. Here's one way of getting delta G naught reaction, which depends on the Gibbs free energy of formation. The other way is to calculate the delta H naught reaction and delta S naught reaction, and then calculate delta G naught reaction. We've done both of these. Okay, we'll look at an example next time how you can go from the equilibrium constant to delta G naught reaction. So this page essentially summarizes everything that we talked about today. I hope to give back to your exams on Wednesday morning. So I have office hours.